as you guys may know, I am a math nerd. And as a math nerd, one thing I like doing with functions, now that we have our triangle functions, is try to graph them and see what we get. We can graph each of our functions separately, and let's start with sine. Now we found in our last example that sine is the height of our unit circle. So we can graph the angle on the x-axis and the height, or the sine, on the y-axis. Now we can see that as the angle grows here until it gets to pi over 2 radians, or 90 degrees, the height just keeps increasing until it gets to 1. So you can add this to our graph here, and then we can see that the height starts going down, and it reaches 0 at pi radians, or 180 degrees, but it keeps going down until it reaches negative 1 at 3 pi over 2 radians, or 270 degrees. So we can add this to our graph, and then we can see that it starts going back up, again passing 0 at 2 pi, going all the way up to 1 at 5 pi over 2, and then keeps going down and up and down and up. It makes this nice pretty pattern too, and it goes backwards too. As you can see, if you start at 0 and you start going down, you get to negative pi over 2, and that's at negative 1. You can go to, and then it starts increasing until you get to negative 3 pi over 2, and then it starts decreasing from there. And you can see you have this nice pretty pattern, but constantly staying there throughout, and that's really all a sine function is this nice pretty curve, up and down and up and down and up and down. And we try this for cosine now, too. Now, cosine is length, so I'm going to turn this graph around when I draw, just so you can visualize it better, compared to the circle. So we can see here that the length when we start the length is 1. However, then it keeps getting smaller and smaller, it goes to 0, and then it goes to negative 1 at 180 degrees, so we can add that to our graph. At pi over 2 radians, it goes to 0, at pi radians, it goes to negative 1, and then it starts going back up. It starts going back to 0 at 3 pi over 2 radians, and then back to 1 at 2 pi radians, and then it keeps going in the same pattern of back and forth, then back and forth. And again, it works for the negative way too, and really, looking at these patterns, this is what math is to me. It's just all these pretty problems with, you'll find these nice solutions and they lead you to pretty graphs like these. Like, remember we got to this just by thinking about the fact that if you select the angles before you make your triangle, then you know what sort of shape it is, but you don't know how big it is. And then we found all these wonderful things. We found the thing with the circle, and we found the thing with this graph, and it's so nice and so pretty. But anyway, that's enough of my rambling. We still have one more function to graph. That's the tangent. Now this is a slope, so it might be slightly harder to visualize, because you can't see it directly on the circle, but you can sort of see how it would turn out. So right here, we have a really long length and a really short height. So the slope's going to be really, really tiny, really, really close to 0. But then it starts getting bigger and bigger, and when it gets almost to 90, that's basically almost infinity. So it's almost reaching infinity at pi over 2 radians, or 90 degrees. But then when the angle is exactly 90 degrees, then you see that, you remember that slope is rise over run. And you can see here that the run is 0. And you can't divide by 0, obviously. So then there's no tangent at pi over 2, or actually at anything that's on this line. So that's pi over 2, 3 pi over 2, 5 pi over 2, and so on and so forth. But then after that, it gets really, really close to negative infinity, because now the cosine is negative, remember? And it's really close to infinity, but now it's the other side. And then it keeps getting smaller and smaller this time until it gets back to 0, and then it goes up and it keeps going to positive infinity, and then it jumps back down to negative infinity, keeps going to positive infinity. Again, you can't have it at the dividing by 0 line, so it jumps back down, keeps going up, and you get this nice pretty pattern of curves. Just curves going all the way up. And now we have all these pretty patterns. But why stop here? Mathematicians started defining more functions to add to our triangle-related functions. I'm not sure why they require different names, so I don't know why you couldn't just say 1 over sine, but anyway. So there is the cosecant, which is 1 over sine, which is confusing because the secant is 1 over cosine. You would think it would be the other way, but I'm not sure why they named it like that. It's a good thing to remember. If anyone knows why it's named backwards, please let me know. And then there's the cotangent, which is 1 over tangent. So then you can draw these by just looking at what is 1 over these functions. So we can start with our sine function again. And we can see that when the sine is 0, you can't have 1 over 0 again. It's just not something that's defined in math. So you can, but when it gets really, really close to 0, all this area, it's going to be really, really close to infinity. And then, but then when the sine here is 1, well, 1 over 1 is just 1. So it goes all the way to infinity, it goes down to 1. And then the sine starts getting closer to 0 again. So the cosecant starts getting closer to infinity again. And then it's the same thing except negative. You draw the same like loop on this side and then on that side. And each sort of bump in the sine has a sort of loop in the, not a loop, a sort of U in the cosecant. And a similar thing for cosine. As you can see, the cosine graph is pretty similar to the sine graph if you just shift it over pi over 2 radians. I wonder why that is. See if you can find out. Why is the cosine just the sine shifted pi over 2? Is there something about the cosine function that makes it like that? What's so special about the pi over 2? Remember, that's 90 degrees. What did we use with 90 degrees when we made these functions? Anyway, so as you would imagine, our secant graph is pretty similar to our cosecant graph. You can see that whenever cosine is 1, the secant is going to be also 1. And whenever the cosine is 0, there is no secant because, again, mathematicians haven't defined a way to divide by 0. But as it gets closer and closer to 0, as the cosine gets closer and closer to 0, the secant gets really, really close to infinity. So you again have these little U shapes going back and forth and back and forth. And again, it's a really nice pattern. Now we can see this again for the cotangent. We have the tangent graph here, and we can start taking the inverse. So when the tangent is 0, you can't have a cotangent, you can't divide 1 by 0. But an interesting thing is that there's places where the tangent isn't defined. There's places where you're dividing by 0 for the tangent. But if you look at the cosecant as 1 over the tangent, that means the cosecant has to be cosine over sine. So cosine over sine in those places would be 0 over 1, which would make this 0 where the tangent is undefined. But when the tangent is 0, you can't have 1 over the tangent, so the cotangent is going to be not there. So again, you have these patterns, and what's interesting is that the cosine looks to be the cotangent looks to be pretty much the same shape as the tangent, which suggests that, like, if you move around the tangent a bit, you can probably make the cotangent out of it. Now we can see Now, one thing I would see is how can we move around this tangent to sort of form this cotangent? How is the cotangent made from the tangent? And you can see if you scoot it over a bit, it almost looks, if you scoot it over the right amount, it almost looks like a flipped version of the cotangent. Or it looks exactly like a flipped version of the cotangent. So let's do that. So we see that we need to move it up pi units. Now, of course, what does that mean? Well, it means that if you take this point here, then you're not actually going to place the tangent of this angle. You're not going to place the tangent of pi over 2 here. You're going to place the tangent of this angle minus pi over 2, or the tangent of 0. You're going to place that here. So for each angle, you're taking the tangent of that angle minus pi over 2. But now it's still a flipped version. Well, how do we make it an unflipped version? Well, we see here that this means it's positive really big, and that means it's negative really big. So all we need to do is just change the sign. So then we find out that the cotangent of some number is the negative of that number, of the tangent of that number minus pi over 2, which I've written out here. Which is interesting because it suggests something about the relationship between the slopes of different angles. If you play around with this property on a unit circle, what do you find out? Let me know. But say I want to make this shape over here. It looks really cool. It's like an infinity sign. Like, I could probably 3D print this and make it into a... I don't know what I would make it into, but it looks cool. So we should figure out how to graph it. So what I'm going to do is I'm going to introduce this new concept, which may be slightly complicated because I'm not going to explain it too well, but oh well. Okay, so what I'm going to say is that it seems difficult to completely relate the x and the y first because there's so many different y's for one x. So instead what I'm going to say is that I'm going to go along the graph like this. I'm going to go do 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 do. And then I'm going to relate. I'm first going to only look at x. And I'm just going to look at when I'm walking around the graph like this, right? When I'm this far along the line, what is my x? So I'll call this far along the line. That's too long. Should call it. What haven't I used? I'll use hat. I like hats. So when I'm hat far along the line, then what is my x? Well, it seems like the x goes up to 1, and then it goes, or the x starts at 0, and then it goes to 1, and then it starts going down, it goes back to 0, and then it goes to -1, and then it starts going back up to 0, and then it starts going up to 1. It sounds familiar, and it should sound familiar because that's how the sine graph progresses. You can graph the sort of, if you graph x based on triangle, you'll see that it looks very similar to the sine graph. See, here I am this far along, that's this far along, and here I am. And now I'm that far along, and now I'm that far along, and now I'm that far along, and now I'm that far along. See, it looks like the sine graph. So we can say that x equals the sine of top hat. Then we have to look at the height. Now the height looks interesting. So we go up here, but we only go up to 1/2. Or we start at 0, the same as the previous one, but we only go up to 1/2. And then we go down to 0, and then you keep going down to -1/2, and then you go back up to 0, and then you go up to +1/2, and then down to 0, and then keep going down to -1/2, and then up to 0, and then 1/2, and you keep going it up and down and up and down and up and down. And that sounds really similar to a sine graph, except you're only going up to 1/2 and down to -1/2. Now first you might think, okay, well usually the top is 1, but now the top is 1/2. So if I just subtract 1/2 from each point, that should be fine. And that would work if only the top changed. But then if you look at the bottom was -1. Now you subtract 1/2. Now that's going to be -3/2. So instead what you have to do is squish the entire thing. To squish the entire thing, you note that what you're getting is not the sine of this angle. What you're getting is 1/2 of the sine of this angle. So then y would just be 1/2 of sine of the top hat. So now you have your two equations, and it may seem weird to have two equations, but you should be able to find in your graphing calculator, there's something called a parametric equation thing where you can submit two equations in terms of a different variable besides x and y. And see if you can put it in your graphing calculator and produce this shape. Or try moving this around, or try making some other shapes, or do whatever you want. Just have fun. Remember that doodling on paper is a lot more boring than doodling on your graphing calculator. And a quick note before I leave is sometimes applying the sine curve to real